let's look at another function and see if we can find global maximum, and we'll start to work in some of those issues that you can have with the extreme value theorem. So here's our function. It is rational. I notice that it's discontinuous at x equals 3, so that's going to be one of the things that I have to check. And then this first interval has one closed endpoint, but the other one is open-ended, so I'll also have to check what's going on as x goes to negative infinity. So my checks will be to take a limit as x approaches negative infinity of this g of x, and to plug 2 into g of x. So this is checking endpoints basically, but since I don't have one on the left, I'll do that instead. And then I'll have to use limits to check out what's happening near, oh, actually I don't. I get off the hook with the x equals 3 because it's not on my interval. So I just need to check for critical values. So if I set x squared over x minus 3 equals 0, you can multiply both sides by x minus 3, and it looks like we have to make x squared 0, which means x has to be 0. So I will need to check g of 0. Okay, so I'm going to do those bottom two. Hold on, I'm being very, very silly. I'm doing what I warned you not to do. If I'm looking for a critical value, I need to set g prime equal to 0. So g prime is equal to the bottom, x minus 3 times the derivative of the top, minus the top, x squared, times the derivative of the bottom, which is 1, all over the bottom squared, which is 2x squared minus 6x minus x squared over x minus 3 squared. We'll go backwards order here, which is x squared minus 6x over x minus 3 squared. You can factor an x out of that. And it looks like this thing is going to equal 0 if x is equal to 0 or 6. So those are my critical values. So I guess I do end up checking 0, so that isn't such wasted writing. I'm not checking 6 because it's not on my interval. So g of 0 is 0. That's what we found here. G of 2 is 4 over negative 1, so negative 4. And then as g goes to infinity, so we want to think about a big number, a million, a billion, a trillion, and say, okay, if we have a million squared over roughly a million, that's going to be a big number, and in fact, the bigger it is, so a million squared over a million is going to be around a million. A billion squared over a billion is going to be around a billion. So the bigger that number is, the bigger this fraction gets, which means the function is going to infinity. If you're not super comfortable with just kind of thinking your way through it like that, you can always use your calculator and plug in some of those big numbers and see what's happening. Okay, so this tells me, this right here, that there is no global maximum. Not possible. If your function goes to infinity, there is no biggest y value. The smallest y value is happening at the endpoint, so this is my global minimum. And then on 0, 6, okay, so same function, but now I have g of 0, and I have g of 6, as things I need to check. And interestingly, those were my critical values, so I don't have to add anything to the list for critical values, but I do now have to worry about the discontinuity, so I'll need limits to investigate that. And in fact, what you really want is to check both the left and the right side. I think I might be making up notation there, but that's okay for here. Okay, so we know g of 0 is 0. G of 6 is 36 over 3. Remember, this is checking y values, so I'm plugging back into the function. 36 over 3 is 12. And then if we want to think about this limit, so it's an x squared over x minus 3. If x approaches 3 from the left, that means this number is just a little smaller than 3, which means this number is tiny negative, really, really small negative number. And then the top is just a little bit less than 9. A number just smaller than 3 squared will be around 9. So if you divide some finite number by a tiny, tiny, tiny negative number, for starters, it's going to make the whole thing negative. Dividing by really small numbers makes things really big. So it looks like As x goes to 3 from the left, y is going to infinity. And then as x approaches 3 from the right, the bottom becomes a tiny positive number. The top is still really close to 9, a little bigger this time. When you divide by a tiny positive number, it once again makes it really big, and this time you don't have the minus sign, so it looks like, ooh, did I just do that wrong? It looks like infinity, and in the last one it should say negative infinity. Okay, so that's going to wipe out the possibility of having a max and having a min. So what we're getting there is an asymptote that goes on the left. So here's x equals 3. This should say x. All sorts of mess here. From the left it goes to negative infinity, and on the right it goes to positive infinity. So that's what we're getting going on here. So no max or min on our interval. It doesn't matter that we cut off at critical values. So no max or min. And that's okay with the extreme value theorem because my function